Assalamualaikum warahmatullahi wabarakatuh. Halo semua, kembali lagi bersama saya Sylvia dari Nainggolan. Nah, kali ini kita akan masuk pada materi baru yang sangat menyenangkan dan bisa membuat pikiran kita lebih kritis, yaitu materi Praktikum Dasar Sistem Kontrol PID Motor DC dari platform Ayo. Nah, sebelumnya saya akan memperkenalkan diri dulu. Perkenalkan, nama saya Sylvia dari Nainggolan dengan NIM 440 2246 53146 dari Prodi Rekayasa Perancangan Mekanik Universitas Diponegoro. Dan kali ini saya akan membahas materi yang sebelumnya sudah kita bahas, namun sekarang kita akan memperdalamnya dengan platform IO Labs. Namun sebelumnya aku mau uh, mau menyarankan kepada teman-teman untuk mendownload dulu aplikasi platform AI Labs-nya di web. Kalian bisa cari platform IO Labs web. Setelah itu, setelah masuk pada aplikasi tersebut akan ada kayak kotak hijau gitu, terus tulisan get platform IO Labs. Kalian bisa klik dan kalian akan dikasih kayak uh, cara-cara mendownload atau diberikan bagaimana alur pendownloadan aplikasi ini. Nah, untuk materi kali ini kita akan membahas atau kita juga harus mempunyai aplikasi-aplikasi ini, yang dimana kita harus punya instalasi FS Code, instalasi kursor AI, instalasi with Surf AI, instalasi Python versi 3.10.12, instalasi extension Python, instalasi platform IO, dan kita juga harus melampirkan link Google Drive panduan instalasi. Nah, tujuan dari fondasi software development environment ini yaitu agar kita bisa menyiapkan lingkungan pemrograman yang profesional, terus membiasakan kita sebagai mahasiswa untuk menggunakan editor modern berbasis AI, lalu kita bisa menyiapkan tools untuk Arduino, terus Python, lalu Excel dan juga grafik. Nah, penggunaan 3 editor AI seperti FS Code, Cursor, with Surf ini bertujuan agar kita sebagai mahasiswa memahami kelebihan masing-masing editor, lalu mampu memanfaatkan AI sebagai asisten coding, bukan sekedar penyalin kode. Nah, selanjutnya uh, Python editor dan AI tools. Nah, Python itu digunakan untuk apa sih? Ya, dia itu digunakan untuk membuat user interface atau GUI. Terus dia mengolah data hasil eksperimen, selanjutnya penyimpanan data Excel, terus untuk menampilkan grafik respon. Nah, versi Python yang dibatasi itu atau yang ditentukan itu agar dia bisa kompatibel dengan uh, PyKT5. Terus dia bisa stabil dengan library scientific atau NumPy, Pandas, terus Matplotlib. Nah, di sini juga akan dijelaskan FS Code sebagai editor utama, terus Cursor dan with Surf itu sebagai editor berbasis AI. Lalu uh, di mana kita bisa mendapatkan uh, aplikasi-aplikasi ini, ya kita bisa dapat di marketplace URL atau link yang diatur agar ekstensinya dapat diunduh dengan benar, terus tidak terjadi error dependensi. Nah, di sini juga mahasiswa kita diperkenalkan konsep AI assistant programming, yaitu menulis prompt, terus merevisi hasil AI, lalu mengoptimalkan algoritma. Nah, extension platform IO dan Python. Nah, platform IO itu berfungsi sebagai boot system, terus library manager, terus upload firmware ke Arduino. Nah, keunggulan dari platform IO itu apa sih? Dia bisa lebih rapi dari Arduino, terus dia juga mendukung project besar atau cocok untuk sistem yang besar, lalu dia lebih profesional dari Arduino IDE. Nah, keunggulan keunggulan kan udah, sekarang extension Python itu digunakan untuk apa sih? Dia bisa menjalankan GUI, terus menghubungkan serial Arduino, terus dia bisa mengolah dan menyimpan data. Nah, terus kenapa kita tidak pakai Arduino IDE saja? Kenapa harus pakai AI terus Python gitu? Jawabannya karena platform IO lebih scalable untuk sistem kontrol yang kompleks atau yang lebih sulit atau lebih besar gitulah. Nah, di sini uh, ada extension platform IO dan Python, di mana prom ini akan menunjukkan desain kontrol yang matang dan mencangkup dari platform IO. Nah, di isi teknis utamanya itu Arduino Mega di mana 2560 dengan pin PWM PWMCW, pin 5, PWMCCW, pin 6, terus encoder itu pinnya 2 dan 3. PID itu dia itu anti window, yang dimana anti window-nya itu sekitar uh, minimal min 255 dan maksimal 255. Nah, di mode ini dia akan memiliki kontrol kecepatan, terus kontrol posisi. Dia juga bisa mereset posisi saat ganti mode. Nah, dia memiliki filter nih, filter yang mana ada filter raw speed, terus moving average, dan ada low pass filter dan speed pass on. Nah, P logiknya atau persamaannya kita bisa lihat KI sama dengan 0, di mana 0 merupakan integral, terus KP merupakan 0 dan P itu juga sama dengan 0, KD sama dengan 0 dan D merupakan 0. Nah, ini juga sistemnya juga teman-teman dirancang dengan matang, yang dimana ada kontrol PID, ya sebelum aku jelaskan kontrol PID, terus filter sinyal LPV, terus LPF, terus ada anti window, terus ada mode kontrol fleksibel. Nah, artinya di sistem ini tuh dia tuh nggak asal jalan aja, tapi dia tuh mempertimbangkan kestabilan dan juga keamanan. Nah, selanjutnya ada user interface Python Qt5. Nah, UI ini sebenarnya berfungsi sebagai apa sih? Jadi UI ini berfungsi sebagai HMI atau Human Machine Interface. Terus dia juga menjadi monitoring real time, terus menjadi pengaturan parameter PID, lalu dia akan menjadi alat analisis sistem. Nah, desain UI dibuat menyerupai software industri, itu bukan sekedar tampilan sederhana gitu. Terus UI ini kenapa sih penting dalam sistem kontrol itu? Karena operator itu atau kita nanti sebagai operator itu perlu paham, memahami bagaimana pengontrolan sistem itu secara real time. Nah, untuk spesifikasi UI itu sendiri, dia itu ukuran videonya harus sekitar 1900 kali 960. Terus untuk panel kirinya itu harus 700 pixel. Bisa disetting. Terus panel kiri kanannya itu grafik atas dan bawah, terus check both show atau hide data, dia itu harus legend dynamics. Terus kontrolnya itu ada beberapa poin, itu connect atau disconnect, dia juga harus bisa memilih port, terus bisa start dan stop, terus clear graphic, ada save PNG, terus ada save Excel dan ini dan poin-poin ini bisa didapatkan, bisa disetting atau bisa bawaan dari windownya sendiri atau desktopnya sendiri. Nah, untuk pengaturan parameter kontrol, parameter yang bisa diatur itu ada set point, terus ada KP, KI, dan KD, terus ada alpha, LPV, terus ada time sampling. Nah, keunggulannya sendiri itu bisa diubah saat sistem berjalan, teman-teman. Terus bisa efek tuning langsung terlihat, lalu dia bisa belajar trial and error tuning PID. Nah, selanjutnya ada history prompt dan debugging. Nah, di slide ini teman-teman kita harus tahu bahwasanya sangat penting kita mengetahuinya karena menunjukkan satu itu proses debugging, terus literasi pengembangan, terus ada kolaborasi manusia dan juga AI. Nah, di sini juga kita ditegaskan bahwa kita harus tahu bahwa sistem itu bagus lahir dari kesalahan dan juga perbaikan, bukan langsung sempurna. Maka dari itu kita jangan langsung merasa gagal kalau proses debugging atau prompt kita ada kesalahan, atau proses praktik kita ada kesalahan. Itu bukan karena kita gagal, namun kita harus selalu mencoba, karena orang yang mau mencoba itu adalah orang-orang yang akan sukses di masa depan. Nah, setelah itu hasil output dari praktik kali ini, yaitu output yang akan dihasilkan itu ada UI PID motor DC, terus ada save Excel, terus ada save PNG, dan program embedded dan UI. Nah, output yang digunakan itu apa aja sih? Itu digunakan untuk analisis performa dari dokumentasi praktikum, lalu laporan tugas. Nah, itu yang akan kita dapatkan kalau kita lagi praktikum. Nah, karakteristik respon sistem itu apa sih? Nah, karakteristiknya itu parameter yang ditampilkan otomatis, ada delay time, rise time, peak time, setting time, maximum overshoot, steady state error. Nah, sistem kontrol itu harus dianalisis secara teoritis, teman-teman. Nah, kita harus dapat membuka teori kontrol, terus data eksperimen, terus respon nyata motor DC. Terus respon sistem yang baik itu cepat atau stabil. Respon sistem yang baik itu harus idealnya itu cepat dan juga stabil. Tapi ya selalu ada kompromi dalam tuning PID begitu. Oke teman-teman, selanjutnya aku akan menunjukkan video bagaimana proses praktikum dari materi kali ini. Jadi stay tune ya.
In this video, we'll see how you can use the newly launched MATLAB extension by MathWorks to directly edit your code in Visual Studio Code. While providing support for editing MATLAB code, the extension includes features such as tab completion, code analysis, code navigation, and more. Getting started with the extension is easy. You can install it directly from the Visual Studio Code Marketplace by searching for MATLAB extension by MathWorks. Now that we've installed the extension, we'll create a simple class that performs some basic mathematical operations. To start, we are going to create a new MATLAB file. We'll begin by defining our class using the extension's class def code snippet to auto-populate the structure. We can just fill in the class properties and methods, and while I do so, you will notice that all the code has syntax highlighting. You will also see that as soon as I start typing, we get a suggestion list, and tab completion helps us quickly fill in the rest. We can use tab completion and code snippets again to instantly pull in the built-in functions we want to use and define the parameters. Now we are going to use tab completion to pull in the round function. If we have errors in our code or some suggestions to improve it further, these will be shown in the problems panel in VS Code. For common issues and suggestions, you can address these using one of the quick fixes suggested by the extension. If you're using multiple functions in a file, you can navigate to the definition of your function using the Go to Definition option, or you can just take a quick peek. Some of the features that we just saw require MATLAB to be launched in the background. If you have MATLAB installed locally and on the system path, you should be good to go. Otherwise, you will need to specify the path to your MATLAB installation using the MATLAB install path setting. The MATLAB extension plays nicely with other VS Code extensions. For example, you can use it with the LiveShare extension to collaboratively edit with others in real time. Or you can try using GitHub Copilot as your AI pair programmer. If you use MATLAB in Visual Studio Code, install the extension and try it for yourself. Any and all feedback is welcome. If you encounter any technical issues or have some great enhancement ideas, let us know what you think by creating an issue on GitHub or sending us an email.
So in this video, I want to talk about how to rewrite a model in Simulink in your Python. So in reinforcement learning, usually we need an environment, and this environment model it's very easy to be set up in the Simulink. However, to set up the communication between Simulink and Python, it does require a lot of effort. So that's why there are two different choices. One, you can simulate your environment in Simulink and then call those in Python. Well, that's something that you can do. We at this moment do not have enough confidence on how it performs. So that's the main reason that we didn't choose this first approach. And we chose this second approach is essentially use the Simulink as a reference and reprogram the environment model in Python. The second choice is, in my opinion, better than the first one, especially when your model is simple. So in my case, my model itself is pretty simple. It's just the the PI controller and a bunch of simple math and the integrators. So that's why I chose the second approach. And in today's video, just as a demonstration purpose, we want to rewrite essentially this model in Python. So what I did is that in order to test this model itself in Python, which is an integrator, I collect the data from my Simulink model as a reference. That's why I was saying that we can use the simulation in Simulink as a reference and reprogram the environment model in Python. So for that, we can essentially play the simulation. In my case, the input to this block is a vehicle speed, and the output is rolling distance. Because my project is a hill hold project, and then by integrating the vehicle speed, I can compute the rolling distance of the vehicle. And to interface with Python, I made it a fixed step solver, because right now I haven't figured out how to use a variable step solver in Python. And the time step is 100 microsecond. In this case, it's also important that we log the format by save the format as array. You can choose to save it to time series, but you may need to write a little bit different function in Python to deal with the data. So let's set this to array, and we already run the simulation. We can actually see that in terms of this data, we have a vehicle speed, and it got integrated into the rolling distance. And after running this simulation as expected, we're gonna get a data file essentially saved as logged data.myt, and I just because I saved it as an array, I renamed it as logged data array.myt. And then after this, I essentially wrote up this script where the file name is pointed to this log array.myt, and then the variable names time, vehicle speed, and rolling distance. So it's kind of important to match the name. It's not necessarily match the name here, but essentially there's a implicit assumption. If you load this data that we let's load this load data array, and then you actually got this data from MATLAB. For clarity, let me actually clear all of them, and if I load array here, I will get a data from MATLAB which contains 3 variables. And the reason it is 3 because there's an implicit assumption that the first one is actually the time axis. That's because we have a stop time 50, and then our fixed time step solver is 100 microsecond. You can verify that by opening the model configuration parameters, and then I already set the solver to fixed step and the step size 100 microsecond. Then you can see that our time is increasing every 100 time step, and then the second variable is actually corresponds to vehicle speed, and then the third one is your rolling distance here. So in my code, I gave it I know it's 3 variables, so I gave it time, vehicle speed, rolling distance, and then there is a function import data from MATLAB array. Is in a separate file. I wrote this function and unit tested it. Essentially, it is rely on the H5Pi, and then it reads in that data array, and then because the file name that we set here is data from MATLAB, so that's why you see this data from MATLAB, and then I just extract all the array and package them into a pandas data frame, which use the name specified here. That's just make it a little bit flexible. If you are collecting additional data here, you just need to match the name in variable names. And it is a little bit more clear if we read the code in Jupyter Notebook. Essentially, we read this as a raw data, and then this can help us extract the whole array, and then we could see that after packaging it into a pandas data frame, we got this pandas data frame that has a time axis, vehicle speed, rolling distance, and then for visualization purpose, I just used matplotlib, and then plotted the vehicle speed versus the rolling distance. So this is a kind of a unit test data created from MATLAB, and we load it into the Python using H5Pi. That's the one that handles the newer version MATLAB files. Because initially I was using something else, from SciPy, and then it was complaining about it cannot handle that, so we have to use that one, and then we could test this actually, by running this file. However, I'll skip that because it's pretty straightforward that we loaded the file into a data frame and then we plot it. And then the in this unit test file, built on top of that, I created this simulation class where essentially what it does is it allow you to set a end time, and it's same to the MATLAB. We set to 50 seconds, and then we have a fixed step solver which have 100 microsecond, and then my model in this case is an integrator, and this integrator I wrote in a separate file, integrator.py, and then that integrator just implement this very simple math that integrate the input and using the time step passed from the from here when you create this object, and then it keep integrating. It also provide a reset function if needed, but essentially what we do is we set up our planned model. This could be more complicated. I'm just using integrator as an example, and then after I wrote the integrator here, at the beginning of the simulation we set the time to be 0 and the time step to be 0. Difference between time and time step is time step kind of keep track of the integer steps, and then the time keep track of the actual simulation time. And then whenever our simulation time is larger than the end time, we'll stop the simulation. And in terms of the simulation itself, right now, first we have to gather the input into the integrator, and here I wrote a function which essentially just get the data from the MATLAB MAT file. If you look at the code here, essentially what it does is we globally already at the beginning of this file we called that function we just wrote, loaded the MATLAB's data into a unit test data, and then the unit test data vehicle speed gonna be the input into the integrator. However, every simulation time step we have to extract a single data, so that's why we pass the step here, the time step to extract the specific input, and then the input at time t, right? We pass it into our integrator, and then the integrator's result can be get from here, and then that's essentially the rolling distance. And I used the list to collect my simulation data, and then I don't need to collect the time, but I create another one, collect the time, and then we just update the simulation time and time step, check for the end of the simulation, and then we can see that we set up a simulation object we call the cycle method. The cycle method essentially what it does is it just keep running the simulation until we hit the end time, and then I essentially also sort of this is the list. Here I just packaged our simulated result into a pandas data frame, and this is some debugging code we could just delete down. And then if the visualization is true, right, we can essentially plot the result. And then I just plotted the result from the Python simulation, which is stored in data unit test all, and I also plotted the data from the MATLAB. So if they overlap each other, I consider we wrote this model, this integrator, successfully. And you could actually wrote additional, instead of visualization, you could just minus the 2 and make sure that they are very close to 0. But I didn't do that. So we can run this code for demonstration purpose. Let's run the unit test integrator.py. So we can see that this is the rolling distance, and the blue one is from Python, the orange one is from MATLAB, and they overlap with each other. So we confirmed that we successfully implemented the integrator into Python, and you could follow the same procedure. Divide your model into different parts, and create different class, and then kind of connect them together. Then you can very easily use this framework to sort of rebuild a simple dynamic simulation created in Simulink using the Python. Just as a recap, here we simulated the Simulink, and we used the data from Simulink as a reference, as a unit test data, and we load those data into the use those data created by MATLAB into the Python, and then we use those data to simulate the model that we programmed in Python. And then we got the result, and we compared that result with against the output result from MATLAB, and then we verified that we successfully implemented that model, in this case the integrator, in Python.